Hi, welcome back to another video. Now, a quick note before we start is I am really trying to make a lot of different types of videos. This is so whoever stumbles across my channel and clicks on it hopefully should have something to watch, whatever their mathematical ability. In this video we're going to take a look at the Gaussian integral, named after who else but Carl Friedrich Gauss, and he was a German mathematician who had many influences on mathematics, and if you study advanced mathematics you will be seeing his name a hell of a lot. So, the Gaussian integral is the integral between minus infinity and infinity of e to the minus x squared dx, and it has a really surprising appearance, or seemingly surprising appearance, of pi here on the right hand side. In fact, we're going to show that this integral is equal to the square root of pi. Okay, so you might be thinking, well, what on earth does the integral of an exponential function have to do with pi? Well, we will see shortly. So let's get started. Firstly, something that's going to be really helpful is to call our integral I. So I'll just write it out. It's the integral of minus infinity to infinity e to the minus x squared dx. Right, the next thing to do is to square this. So I squared is the integral squared. And this, of course, is just the integral multiplied by itself. Now, you should know from ordinary calculus that when you're looking at an indefinite integral, the integration variable doesn't really matter. So what I'm trying to say is that this is exactly equal to the integral from e to the minus x squared dx times the integral from minus infinity to infinity e to the minus y squared dy. So this integral here and this one here are the exact same, because when we evaluate our limits we're going to get the same answer anyway. Okay, so this is good. So what can we do with that? Well, we can bring the integrands in together. So we get, it's going to be a double integral. So it's minus infinity, infinity, minus infinity, infinity, e to the minus x squared plus y squared dy dx. So what have we done? Well, we've just multiplied these two functions. When you times two things that have the same base, you add the powers. So it's e to the minus x squared minus y squared, and we've just put it in brackets there. Right, good. So this is what we've got so far. We've got I squared is equal to the double integral over the whole real line, e to the minus x squared plus y squared, with respect to y and x. But how does this help us? Now, here is the part where you might sort of suspect a little appearance of pi. We're going to change to polar coordinates. And in order to change to polar coordinates, we let x equals r cosine theta and y equals r sine theta. And then, because we're changing coordinates, this is integration by substitution after all, we want to eliminate this thing here, x squared plus y squared, and hopefully you can see that this is going to be equal to r squared cos squared theta plus r squared sine squared theta, which equals r squared, and let's factorize, so we get sine squared theta plus cos squared theta, which just equals r squared, because sine squared plus cos squared theta is 1. Okay? Good, so what have we got? We've got x squared plus y squared equals r squared. And why do we change to polar coordinates? Well, in cases such as this, it allows us to integrate easier. Right, good. So if you're not familiar with polar coordinates and why they're useful, there will be many videos on YouTube. So just go and search one of them. And also, if you've learnt calculus, you should know about polar coordinates. One other thing we need to consider when doing polar coordinates is this thing called the Jacobian. Now what this does Right, we need to change this dy dx into something involving dr and d theta. And what the Jacobian does is balances everything out. Now, to calculate it is pretty simple. We just find the determinant of this matrix. And we need to take some partial derivatives, so it's dx by dr, dx by d theta, dy by dr, dy by d theta. So hopefully you're familiar with partial derivatives. So this is the same as the determinant. Well, dx by dr is just cosine theta. Dx by d theta, cos differentiates to minus sine, so this is minus r sine theta. Dy by dr is just sine theta, and dy by d theta is r cosine theta. And this is the determinant. So determinant, we multiply top left by bottom right, take away top right times bottom left. So this equals cos theta times r cos theta, take away minus r sine theta times sine theta. So this equals r cos squared theta minus r sine squared theta. There we go. And so this equals r. So this means this is the factor that needs to go in front of dr d theta to make it equal to dx dy. And again, if you don't quite understand why we've done that, go and watch a video on polar coordinates. Okay, we're almost ready to transform our integral now. We just need to consider the limits. Now, we're integrating over all of r squared, so that's the real plane. And because we're changing to a circle, this means that we're going to have a circle of infinite radius. So don't forget, the smallest the radius can be is 0, which is just a point, and the biggest it can be is infinity. Right, and because we're in a circle, theta must be 0, and theta is 2 pi. So now we are ready to transform our integral. I'll just write down the other bits. So we had x squared plus y squared equals r squared, and dx dy equals r dr d theta. Okay, good. So our integral I squared now becomes, it's still a double integral. So on the outside, we're integrating with respect to theta. On the inside, we're integrating with respect to r. So we get e to the minus r squared. And don't forget, dx dy is r dr d theta. Good. Once again, we're going to use integration by substitution, and this is going to help us solve this inside integral here. So we're going to say let s equal to minus r squared, and then we need to find an expression for dr, so we differentiate, so we get ds by dr equals minus 2r, and this tells us that dr equals minus 1 over 2r ds. Okay, great. We also need to look at the limits, so when r equals 0, s equals 0. When r equals infinity, s equals minus infinity. And now we are good to transform that integral. So this is what we get. We get I squared is equal to, the outside integral doesn't change, so we're still integrating with respect to theta there. The inside, where we had r equals 0, we have s equals 0. Where we had r equals infinity, we have s equals minus infinity. E to the minus r squared now becomes e to the s. We've still got an r, and we have dr, which is minus 1 over 2r ds. And we're still integrating with respect to theta on the outside. Okay, excellent. This is where we're at. Hopefully you can see that this r and this r here cancel. So we're left with integral 0 to 2 pi minus infinity to 0 e to the s over 2 ds d theta. Sorry, minus e to the s over 2. And one more thing we can do. When we have this sort of thing happening in integral sign, where the top value is lower than the bottom value, we can flip them around and add a minus sign, like so. And this is just a basic result of calculus. So we get minus infinity on the bottom, 0, minus e to the s over 2, ds d theta. These two negatives are going to cancel, and now we can work this out much easier. We're now able to integrate the inside function, but we still have the outside integral. So e to the s over 2, this just integrates to the same thing, e to the s over 2. And we're going between 0 and minus infinity. We still respect to d theta on the outside. So this middle thing, we're going to get integral 2 pi to 0. E to the s at s equals 0 is a half. And we're taking away e at minus infinity, which is going to tend towards 0. D theta. We're almost there now. So now our function I squared has just boiled down to the following. 0 to 2 pi, a half, d theta. A half is just a constant, so this just goes to a half theta between 2 pi and 0. So this just equals a half lots of 2 pi take away 0, which equals pi. And don't forget this was I squared. So because I squared equals pi, this tells us that I equals the square root of pi. And we are done. So hope you enjoyed that. Hit the like button if you did. Bye bye.